Great to be here. My name is Ludwig. I'm the managing director at Alexium. We're a legal decisions predictions company, and we use artificial intelligence to predict the outcome of legal decisions. But today I want to talk a little bit about chatbots because this is a bots conference. And my feeling is that there's quite a lot of different people in the audience, and it's a little bit difficult always to get the right content for everyone. So I want to make sure that every single person in the live stream gets something from this. So we're going to spend some part talking about computing theory. We're going to spend some part talking about high-level linguistic theory. And then we're also going to be talking about use cases for chatbot in that order. So I'm going to get started. I'm going to share my screen with you guys. And we'll hop right into the presentation. Okay, here we go. File. And present. There we go. Okay, let me just verify that that's sharing quickly. Yeah, that's fine. Okay. All right, so let's get started. So the overview is, first we're going to talk about some theory. We're going to talk about what solving law means, because at Elixir, that's our mission. We want to solve law. Then we're going to talk about language games, which is a specific concept that we use at Elixir to increase accuracy on our downstream tasks. And then we're going to go over to practice. And we're going to talk about chatbots, which we've had some experience with building. And essentially here, I think there are two kind of main choices that you can make. And there's some tech choices and there's some functional choices. And whichever one you go with on either also kind of, influences your decision on the other. Finally, we'll talk about the practical implementation of some chatbot examples, and then we'll get to the conclusion. Okay, so solving law, right? This is a very, kind of broad idea of what we're trying to do at Elixir. But essentially, the question for us is there an objective dimension to legal knowledge? To give you a concrete example of what that question means, so for example, we have a case that goes to court, and we can record that case using factual description and legal description. The question that we have at Elixir is it possible to train an algorithm to take that as input and produce the correct answer that a judge would give? And our basic assumption for building this kind of system is that, of course, there is one correct answer for a judge to give. That's something that's hotly disputed within the legal profession, and this gentleman you see right here is somebody who would agree with us, right? Now, encouragingly, we've been finding some really great results. We have had a number of different tasks that judges do, and we've been able to automate them completely, achieving accuracy scores in the high 90s, right? So it's near human performance, and on some tasks, we're actually beating lawyers at making these kind of predictions, which is good for the legal profession as a whole because it, validates the assumption that there is an objective dimension to legal knowledge that you can model, but it's also kind of bad for lawyers because it shows that they don't really understand what the objective dimension of their own profession is. Right, but essentially this it's a question of language, right? And all the techniques that we use to build these models are NLP techniques. And this idea of a language game is something that I think is incredibly important to natural language processing. And it's also something that's very easily overlooked within the field. Now, before we get to the concept of language game, there's one other concept that I want to introduce and that we need to introduce. That's the concept of dense word vectors. So this is for everybody who likes a little bit technology, likes a little bit the computing theory behind some of these algorithms. So the idea of dense word vectors, so first of all, why they're called dense? They're dense because there's a value at each part of the vector, as opposed to having simply, one value representing that word ID in a vector, right? So there are two different ways in natural language processing generally that you can represent a word. You can either represent it as an ID, which is then saved as a 1 in that vector and all the other ones a 0, or you can represent it as kind of dense word vectors, where every single value is actually one numerical value that's not 0. These are usually much lower dimensional, right? So you would have maybe like 100, like the usual examples are 50, 100, or 300 dimensions, sometimes 200 as well. And the idea is that instead of simply, giving a word an ID in these very high dimensional hot encoded vectors, we actually want to have these word vectors to capture a lot of the semantic content. And the fun thing about this is that we can then use that information to make operations and to find out, to kind of plot the semantic similarity between different words, right? We can subtract words from one another, and that gives us interesting relations. Now, this formula that you see here specifically, now intuitively what it does is that we're trying to get an analogy, all right? So let's say I give you 3 words, and I'm asking you to find the 4th one. So we could say man, woman, and king, and then we're looking for the 4th word, right? Same example, man, woman, actor, right? We're looking for a 4th word. And actually what this formula intuitively does is it allows us to find that 4th word, and that 4th word based purely on the word vectors of the words that we're trying to find the analogy for usually fits the semantic relation as well, right? So essentially, if we take man minus woman, and that's the vector path in vector space, right? That's the path in vector space from the word man to woman, and we take that path and go the same path from king, we get the word queen. Right now, I'm just going to let that sink in for 1 second, because it actually means that we can plot the semantic relationships between words mathematically, which is just nothing but short of revolutionary for linguistics. So to just fulfill the other example as well, if we take man and we subtract woman, then we have a path in vector space, and if we add that vector to the vector for actor, we get the vector for actress, right? And this is super interesting also for us working in the law and in legal tech, because obviously it allows us to kind of, basically put legal principles and legal problems into vector space as well and do operations with them, which is super interesting. So let's get back to language games, right? So language game, that's essentially an idea propounded by Ludwig Wittgenstein, who's probably the greatest linguist of the 20th century. And I'm mentioning a lot of linguistics as well, because I find that too often computer scientists and people working in natural language processing see themselves as computer scientists first and linguists second. So I'm not saying it should be the other way around, but you should have a feeling for both, right? Because you are working with language, and language is complex. And you're not going to be able to solve perfect, you're not going to be able to solve language if you're simply, looking at backpropagation, building some models in TensorFlow, right? You actually have to, I think, engage with the domain that you're working in. So Ludwig Wittgenstein essentially said that we should think of language as kind of not consisting of one single entity, but of one large entity composed of a kind of complex structure of multiple little language games, right? So a language game would be something where 2 participants communicate, and they're able to share information because they have the same background assumptions. And if they don't have those background assumptions, then they can't engage in this language game, which allows them to even transfer information correctly, right? Because language has an open texture, and it's sometimes very difficult to understand the context of something. So you have to have these common assumptions, common background assumptions, in order to share information effectively via language. Now, at Elixir, we believe that law is, of course, a special kind of language game, and that makes intuitive sense as well, because if you look at problems, for example, in the criminal law, where you have a word like intention, this word has a very different common layman meaning from the word intention in the criminal law. Now, what we've done at Elixir is we've taken this concept of word vectors, of dense word vectors, and we've investigated whether or not we can plot that difference mathematically as well by training our own word vectors on our own legal data, right? So we're using global vectors for word representation, which is from the group around Chris Manning in Stanford. So it's just a special kind of model how you would train these word vectors using a co-occurrence matrix. If you want the kind of details, just look it up on the internet. You can just look for global vectors, and also for Richard Socha. But essentially, what we found really is that when we have a certain task, like let's say we have our algorithm that makes a prediction about whether or not a specific complaint was upheld or rejected by an ombudsman in the UK, then we can increase the accuracy of that downstream task by multiple percentage points, simply by using our own word vectors that we've trained on legal data, as opposed to word vectors that were trained on Common Crawl, right, or on all of Wikipedia, just like a huge corpus of normal text. Now, what that suggests, of course, is that law is a special language game, and that the way that semantic information is stored in words and language, in law, is fundamentally different from the way that information is stored in language in other areas of language, like, or in just common usage. So this is, you can kind of then think of going down a little bit further, going even more low level, and thinking, well, why don't we train these global vectors not just on one like law corpus, but on a specific area of law? Like if you have a criminal law problem, then you can just train it on criminal law data if you have enough data. And intuitively, that seems to be a good approach, which we're looking into at the moment. Now, just as a kind of technical, add, here's again for some people who are actually working with this. Our approach really is that it's good to train your own word vectors first if you have a lot of data, and then either make them non-trainable or trainable. Of course, some people might say that you can start with the normal word vectors anyway, but make them trainable parameters in your neural network, which is it's a fair approach. But we've actually found that because initialization in the matrix matters quite a lot, it's actually useful to use your own word vectors even if you're going to allow them nonetheless to be trained. Great. So key takeaway from this kind of part is that we should think of language not as a single huge entity, but composed of different language games. And this also should be reflected in our approach to building these models. All right, next I'm going to move on to the practical side, right? So chatbots. So how do we build them? When are they useful? So in this basic idea, right, this kind of screenshot I have here is it's from a paper that was published in Stanford, which is essentially using two chatbots to speak with one another using deep reinforcement learning. And just to kind of that this is pretty much state of the art right now to have two chatbots chat with one another. There's no real use case, I think, at the moment for having two chatbots speak with one another, but just the technology is still really in its infancy to build generally conversational agents. I just don't buy this whole Mitsuku winning passing the Turing test and winning all of these awards, because those are just rule-based systems. And I think in the end, right, so I think there's two technical choices that you can go with. You can either build deep learning systems, complex neural network architectures, using deep learning, deep reinforcement learning, LSTMs, convnets, whatever you want. And you can use this to build generally conversational agents. Or of course, you can just make these rule-based systems. And these rule-based systems, of course, aren't AI in the traditional, I guess, definition of AI, if there is one. But they are able to perform a certain task, right? And while generally speaking, so I think there's actually a lot of hate for these rule-based systems because people say, oh, it's not like state-of-the-art technology, and like these things are very difficult to build. They take a ton of time to build, and they take a ton of time to maintain. And that's true, fair enough. But at the same time, I think that the ball then goes to the other side, to deep learning architects, and build me a system then that works better for what I'm trying to do. And that's not always given that works, right? Because we're just not far enough in building conversational interfaces and with deep learning architectures. So I think that, but to move on a little bit to why this distinction matters. So this is kind of the challenge you're up against as somebody who builds chatbots, right? Because this is what's called the uncanny valley, right? So this is essentially, it just plots how human a robot, an image of a robot seems, and how empathetic you are towards it as a human. And what's interesting, of course, is this uncanny valley region right here, where it's just before it looks really human. People tend to really suddenly dislike the thing that they're looking at. Now, of course, my idea for how it goes with chatbots is the uncanny valley probably starts somewhere around here, right? And then people hate it all the time. And then, at some point, maybe if we reach 100%, people will like it. But people generally like to screw around with chatbots. So you really have to plan well, and you have to define your goal, right? So this is just an awful, horrible example of what the uncanny valley looks like as a picture. I think that's really frightening. Okay, moving on. So the reason why I show this is because essentially with chatbots, you have this functional choice as well, which is, do you want to build a conversational agent, which can talk about a lot of different things and kind of, responds to random input and wants to, speak with people like people speak with one another. In that case, you should go with a deep learning architecture, but make sure that you're kind of mitigating expectations, because still a lot of the time, even though your bot might be able to speak about its brand or speak about your brand or kind of provide some useful information, there's not going to be a great conversation that comes out of this at this point. And the other choice is, of course, to build an expert agent. That's really when you have a chatbot that's supposed to do one thing, right? Like send money to one person or get you to the right website, a part of the website, right? or kind of, give you some information about something specific. And in that case, you got to go with the rule-based systems. Simply, I think, because if you define, I mean, you don't have to, of course, right? But I think it's the better choice for these things, because if it's clear how you can get your user from the starting point to the end goal, then having these rule-based systems is a good approach. And then you can add some NLP sometimes, a little places where it's useful. So for the practical implementation of chatbots more generally, I think you have to define your goal really well, and then you choose your functions on the basis of your goal, right? So you think, what's my goal? What do I want to get from having a chatbot? And then you decide which architecture to go with and which paradigm to go with, and also, which kind of a conversational or expert system you want to go with based on what your goal is. So the form, I think that's the main takeaway from the practice side, is that the form follows the function. Now I'm almost out of time, but I just want to briefly mention the abducted by aliens problem, right? So this is essentially my personal advice. If you can use a form to get information from your users, and there's no reason for you to use a chatbot, then don't use a chatbot. And the reason for that is simply that, when people look at a form that they're supposed to fill in, they're not really tempted to write things like, I was abducted by aliens, right? Or, what's an aardvark? But unfortunately, when you have a chatbot, people tend to like to say these kind of things. They like to say, oh, I was abducted by aliens. So, and if you're not a good chatbot architect, then this is going to lead to really embarrassing results. But in any case, you have to prepare. You have to prepare for these things. Great. So I'm out of time. And the conclusion, essentially, from the theory part, is we should think of language not as one single structure, but as like a complex structure with different language games. And for the implementation of chatbots, I think it's important to have form follow function. Great.